So last time we discussed e to the x and log, and we also mentioned laws of logs. When you have a product, log is so fascinating that it slows down the product by breaking it into sum. For division, it slows it down to breaking it into difference. And then if they have a polynomial... Thank you. See, it's the first row responsibility to mention that. And if you have an exponent, good job, extra credit on the final exam, then it also slows down that. Instead of exponent, now there's a product. So how can we use that in practical questions? Let's do this example. This is what you have in your homework. In your homework, you have log, well, there's a limit. Limit of log, ln. Every time I'll say log, I will mean ln in this time. 4 plus 9x minus log 2 plus 5x. X goes to infinity. Okay, first of all, do you remember what ln is doing at infinity? What is ln x when x goes to infinity? Do you remember that? It's not very trivial. Goes to infinity. Like we just covered last time using graphs and ideas. But here's the graph. Log slowly but surely keep growing forever. It doesn't stuck anywhere. But also remember, I gave you, there's a video I have, and I mentioned before when we were talking about limits at infinity and infinite limits. Log, so we have list of functions, and they are slow or not slow when you compare them to each other. So x squared at infinity, infinity. E to the x at infinity, infinity. Log at infinity, infinity. Sine at infinity is surprisingly not infinity, and so on. So log is also infinity, infinity, but it's the slowest one. So log is a slow function. It will be important even with integrals later and with approximations. Log is a slow function. So infinity. Well, then it means this guy is infinity and this guy is infinity. Okay? Last time I mentioned if I say infinity, we mean plus infinity. That's the international notation. So we have infinity minus infinity. Minus infinity equals to 0. Problem solved. What's the problem here? Do you remember? What is the issue? People at the back, do you know what infinity minus infinity is? Yes? It doesn't always equal to 0. One infinity can be stronger than another one. They might have the same rate or so on. Yeah, you cannot do that. You cannot claim infinity minus infinity is 0. So we have to figure out a different method. And that's what we're going to do. We're going to use laws of log. Laws of log says if you have ln minus ln, then it will be 1 ln. It's like we're collapsing it into one log. 4 plus 9x over 2 plus 5x. Does that make sense? Laws of logs. Difference becomes quotient. Remember, it's not log over log. So that's an important thing to mention. Students tend to make this mistake. They think log 5 minus log 7 is log 5 over log 7. So the idea is log takes inputs and plays with the inputs. 5 over 7. That's important. So it plays with the inputs. There's actually no formula about what to do log over log or log times log. There's no formula for that. It's only playing with the inputs. So this input over that input. First one over second one. And now you might remember from limits or not that for functions where limits exist and limit of log exists and limit of this fraction exist, you can submerge. I don't know what's the right terminology to use here. You can tell me. Submerge this guy inside. What kind of term would you use? It will be limit or log of limit. Now, x goes to infinity. Any interesting English terminology you can share? Inserted. I like that. Being inserted. Anything else? English has, I think English is one of the biggest languages in the world in terms of synonyms, because English has French and German and who knows what.
English is 3 languages stacked on top of each other.
Yeah. English even have Russian words in it. For example, Sputnik used to be satellite because USSR were the first one who sent the satellite. So it was Sputnik, but then the Americans got angry and they renamed it to satellite. And then also babushka, you know babushka. It's not babushka, okay, it's babushka. It's really not right to say babushka, but every movie says it, so now it's too late. John Wick. And then also piroshki. But it's not piroshki, it's pirashki. I don't know why Russian words in English do not sound right. It's just so weird. But this is the word that were adapted, so they were not changed.
Even Mexico has Mexico.
Yeah, Mexico. Of course, yeah. So that's why. No other synonyms. So submerged, inserted, injected? I don't know. Anyway, did you solve this problem while I was talking? You remember how to deal with the limits like these. Find the leader of the top, find the leader of the bottom. If the powers are the same, the answer will be the ratio of the leading coefficients. So the answer is 9 out of 5. Correct?
Won't we put ln in front of it?
ln. Don't forget that, because students get excited and they put 9 over 5, but actually it was inside of the log, so don't forget about that. Boom, that's the answer. Yes?
So can this be done with other functions? Like if we know the outer one goes to infinity, can we just find the inner one?
Yeah, if the outer one goes to infinity. Actually, good question. Can we move the limits inside if it's not finite? No, the laws of limits worked if limits exist. That's a good question. In these questions, we will be working with logs, and actually, let's check this one. Maybe it will help you. Example number 2, that's also from your homework. How to work with limit of sine. Oh, wait, do you guys have questions about this beautiful idea of submerging, injecting, copy-pasting limit inside of the log? Then, this is a good exam question, by the way. Like, this is a very classical exam question. So just letting you know, put a star. I always tell students, put a star. It might show up on the exam. It's very popular for the exam. How about this one? This one has function inside of the... Instead of log, there's a sine. So there's a function inside of the sine. Let's do the same thing. We don't even need to be bothered with logs this time. A limit will go inside because sine of limit exists. Well, also, those functions are continuous, so it's also nice to have that. So we're going to have limit of 5x plus 3, 3x minus 1. Sine is waiting for the limit to be solved first. Then the answer will be 5/3 again, and it'll be sine of 5/3. Sine of 5/3. Agree? Limit of sine at infinity actually does not exist, but in this case, yeah?
And that's what I wanted to ask, like, shouldn't we just like look at the first thing, that's sine x, and like ignore the part under the sine for a minute, because anyways sine at infinity is like not defined, so no matter what, the answer should be not defined.
Oh, very good question about that. Sine, let me try to explain. Sine at infinity, or basically x, when x approaches infinity, does not exist. If you don't remember why, the vague explanation, because it wiggles forever, so it never stops at any moment. It's keep wiggling. That's a wave, basically. So input at infinity is not always infinity. If I put sine, maybe that will help you to understand, 1 over x, it changes the input. Even though x still goes to infinity, now the input is 0, and that gives you 0. So you need to take into account what is the input. Input takes you infinity and maybe redirects it, shrinks it, becomes a ratio of 5/3 in our case, and so on. Yeah?
So once x becomes a rational function and there are restrictions to, or like not restrictions, but like places where x cannot be defined, that's when we can find the limit of sine.
Oh, very interesting. When x cannot be defined. It's
in the earlier question, we know that x cannot be 1 over 3. Because that would just...
Oh, that's clever. That's you going in the opposite direction. I like it a lot. This is the different question. What would be with this limit if x approaches, what did you say? 1/3 sine of the same fraction. Now it will be sine of either infinity or d and e, and the answer is d and e. So it matters. It matters what is happening. Well, now if we plug this, denominator gets 0, and actually it's a whole. So it's, let me think, probably it doesn't exist. It probably doesn't even infinity. So it will be d and e in this case. Oh, the idea is the same.
At that point, it just means that x does not exist, but after it would still.
This is how you see it. You cannot, if we go back to, I can actually go back because I have all the notes here. This might explain. When we talk about limits, we had laws of limits. That probably is a very good thing to mention. Laws of limits, here they are. So we're talking right now about the limit inside of the function. Something about these ones. So that only happens if limit exists. Since limit of that fraction does not exist, then you cannot merge it inside like that anymore. So you can play, I guess not professionally I would explain this, but you cannot play with limits if even one of them does not exist. That messes up everything. So existence matters. That's why it says here, limit exists. Like so. Both, what are the difference here? And a limit exists. So then you can submerge, like in this case, we did limit inside of the n, and n stayed outside, or a square root, and so on. Also, we had some kind of homework examples in that chapter with the same ideas. Yeah. Does that make sense? Very good question, people. Very nice questions. Continue. One more thing is a little bit more boring, but you need to know how to do that. There's no limit here. That's a classical exam question as well. What to do, how to deal with this log. The question tells you to break into smaller logs. Big log, break into smaller, tiny logs. That's also a very American thing to teach. They like asking students to play with logs, which is fine, I guess. It's just a kind of tedious work. So what they want you to do is to be very comfortable with laws of logs. Okay, let's do that. Why not? Let's remember what is happening here. We just remember that if you skip the class, let me tell you, x times y becomes ln x plus ln y. It takes input that had product and breaks it into sum of two logs. And then, as I mentioned before, if you have x over y, then denominator will be just negative log, like so. So it works really well with products, quotients, and powers. The last one is ln x to the m is m ln x. So those are my laws of logs. I'm just reviewing them, and that's not new. So what it does, it knows it's a polynomial. It knows it's very fast function, and it slows it down by creating, instead of the power, it creates a product. So that's very nice. So log is very good in creating slower processes, slowing down the process. Okay, good. I can do it in a fast way or in a slow way. I'm first going to do it fast, and then I'll do it slow. So this is how I learned it when I was learning the laws of logs myself. I remembered that everything on the top will be first when it comes to fraction. So I'm just going to write down ln of the numerator. ln of x to the 4 times a square root x. I guess I will do slowly. I just realized. It's fine. Minus everything in the denominator will be minus ln of that denominator. So log treats this fraction as two parts, numerator and denominator, and takes numerator and then subtracts denominator with logs in front of them. Then that's not all. Then I noticed there is a product inside here, and that's when I actually would skip the step and write down log plus log right away. So the first log becomes two logs, ln x to the 4 plus ln square root of x minus 1. The last log is now just staying there. Don't touch it. There is no formula telling us what to do with sums or differences inside of the log. There's no formula for the log of sum or difference. So whatever is inside should stay as it is if it's not a product or quotient. Still not done. The last rule to use is the power thing. It takes this power and puts it down. It takes this power. What power is that? 1/2 and puts it down. We have 1/2, and that's the final answer. ln of x. No, the first one is a 4. 4 goes down, ln of x, and then 1/2 goes down, ln of x minus 1 minus ln of 3x minus 4. That is the last step. This is the answer. How about that? Is it too fast? Let me know. Is it too fast or not? Sometimes I go too fast, so you need to tell me if that's the case. Whatever was at the top will be log plus log. Whatever at the bottom will be minus log. Powers, put them down. Don't forget to rewrite x minus 1 as 1/2. 1/2 goes down. If you know how to do it, that should be your favorite problem on exam. But if you don't, then it's one of those problems. If you know it, it's kind of not hard to do. But if you don't know, then it's hard. Questions, ideas, critics, suggestions? Nothing?
Can we say that ln can be multiplied inside 3x and like minus 4, like it can be distributed?
Yeah, so there's no formula for that. Very good question. I'm glad you asked. Let me write it down. At the very end, there's a note. There is no formula for x plus or minus y. There is nothing.
But like, can we just distribute ln x plus ln y?
ln x. Yeah, you cannot. There's no formula like that, unfortunately. Yeah. There should be a formula, so it cannot. It doesn't do that.
No, but like, if we treat x and y as a number, and then if we add the number and then add ln in front of it, can't we just like write ln x plus ln y, or like
So
like treat
5 plus 3, like so? Like so?
Yeah, so like this equals.
Yeah, it cannot. So remember, you cannot do that. There's no formula for that. There's only formula for the product and quotient, not for sum and differences. Remember, like we're saying with a sine. Sine of 5 plus 3 is not sine of 5 plus sine of 3. After all, do you know what sine is? It's normal function, but it's so popular it got a name. It was named sine. Sine, S-I-N, is a name. It's a title. It's like Julia, name for the function. Log is a name too. It was created and they call it ln or log. So some functions cannot break into pieces. Yeah, this commutative properties and so on. So very good. Thank you for asking. Inverse functions. Let's quickly cover that. I have a whole PDF file on inverse functions and video, but I will just briefly tell you what it is. Inverse functions. Because I want to move on to derivatives, because that will be covered in all 3 exams. Exam 2, exam 3, all 4 exams. Exam 2, exam 3, final exam, and master exam will be about derivatives. So we'll have lots of derivatives. So inverse function is not such a popular question to be on a test. That's why I don't like to spend time on it. But if you remember, do you remember horizontal line test, vertical line test, those things? So I like drawing this cute picture to explain you what inverse function is. If you have, that's going to be a definition, I guess, f of x equals y, right? Or y equals f of x can be reversed. What if I want to have input standing outside versus output? Well, then it will be x equals f inverse of y. Minus 1 at the top doesn't mean 1 over f. It's reserved for the inverse function. This notation means if and only if, or basically it's a formula, so it goes both ways. Put this in the box. Do you know what I just did? I applied inverse to both sides. F at F inverse of x is x, and vice versa. So what I just did is applied inverse to both sides of the equation to dig out the input. That's because that is the whole point of inverse functions. They are undoing what the other function was doing. The only difference, just a second, is for the, that is the confusing part, that here, for the first example, x is in the domain, x in the domain of inverse. Let me see. F is the domain of f. No, inverse. Yeah, inverse. Because we're talking about inverse inside here. This x is input for the inverse, while this x was input for the original. So apparently that's not the same thing. You will see it later, and I'll explain in a second. In the domain of original f. So remember, f inverse is not 1 over f. This notation is strictly reserved around the world. Isn't it interesting? It was created before internet and before planes, if you think about it. And people agreed suddenly that f minus 1 is not 1 over f. It's inverse function.
Oh, that was my question.
Right? Isn't it amazing? So mathematics has that.
I thought,
Yeah, that some kind of agreement happens. I always feel fascinated about this fact.
so if you wanted to 1 over f, is that you have to put it?
You have to write it down. There are two ways to write down 1 over f. Either 1 over f, or you write down f, everything to the minus 1. So that's very rare you will see notation like this. People just don't write it down. They write down 1 over f. Yeah. But it is fine. So here's your ideas of the inverse functions. Undoing what was done. And you know some inverse functions already. Which one do you know? Y equals sine x. But wait, what if I want to know x? I'm gonna apply to both sides inverse function. It will be arc sine, which is called sine minus 1, sine minus 1. I will apply it to both sides. And it becomes sine minus 1 y equals x. You see, I'm digging out the input. I want to know what is the input. And it goes both ways. Sine minus 1 is also reserved for the arc sine, inverse sine, not for 1 over sine. So this is a reservation in general for this new notation. Now, blah, 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 composition of functions. Let me show you a beautiful graph. And then while I'm showing you the beautiful graph, I will explain you the cool idea of inverse problems. So composition of. I will show you what I'm trying to recreate. Look at this beautiful graph I did. Look at this rainbow, amazing graphs. Composition of inverse functions. Inverse functions. If you have, so function is a machine. We like to describe it as some kind of machine. I like to draw it as a little candy, but actually it's a machine. You drop something in this machine, it's doing some process, and then it gives you the result. So the process is called f. It can be anything, square root of log over sine. It can be differential equation. Maybe 55 equations. It's still input. It swallows x and gives me what? Y. That is the idea. Swallows, spits out, right? And then y is not necessary. Y, it can be t, time, and can be gravity, who knows, z also. Why not z? So usually people just call it f of x. That is more general. It's f of x. What happens if after this I'm gonna throw it into the next box? And the next box will be f minus 1 inverse f machine. First of all, it will look differently. Like, say, like this. I don't know, just create any kind of machine looking thing. It's like a robot machine. And now I'm throwing it at f minus 1. That's inverse. It's working on this y, which is f of x, and spits out back x. That's what it's doing. It's undoing what previously was done. And the other way around, if I threw y into machine of f minus 1, it spits out x. Then I threw x into f, it spits out y. So that's a cool process composition of two functions. And we already mentioned that the graph looks like so. If I have a function, and your favorite function, for example, is, let's say, square root of x. This is how y equals square root of x looks like. At 0, it is 0. Negative numbers, not in a domain, goes slowly increasing. Still increasing faster than log, by the way, but pretty slow. Log is like this, you know, and then they kind of look the same, close to each other at some point, but then log is still slow. To draw this function, you take a ruler and you draw y equals x as a helping tool. Y equals x is your mirror, something you use to reflect the function. That was a reflection chapter in pre-calculus class. So that is called y equals x, which makes sense because we want to change x and y. That's literally what the whole idea of inverse function. We want to dig out the input when the output was known, or we want to dig out the output when input was known. And now you symmetrically draw new function, which is now inverse of, in this case, it will be, let's do f equals, let's do x. And what is the inverse of square root of x? Do you know the inverse of square? Guess. What is undoing square root of x? X squared. Isn't cool? So, reflection. It's a reflection. The only interesting thing, and it's kind of unfortunate, x squared doesn't look like this. X squared looks like that. That's what parabola is. However, when you work with inverse functions, it kind of messes up with domain. Apparently, it sometimes restricts domain. Restriction. How to write down restriction? How to write down restriction? I, right? R-E-S. R-E. Restriction. Restriction. Thank you. I keep forgetting. I or E. Restriction. Do you know how hard it is to write down the word assignment? Every time I make an announcement, it's like 1 out of 5. I'm writing it down correctly. Assignment. Try to write down assignment as a foreigner. Do you know how hard that word is? It's crazy. Do you know that word committee has 2 E, 2 M, and 2 T? Crazy.
Oh, my mom had a trick for that. She also learned English as a second language. She always remembered it as segment.
Oh, me too.
A segment what?
Assignment as a segment.
A segment. Oh yeah. I learned it assign, so I finally remember assign, and then meant. But also engineers. The worst, you know, there's lots of jokes about nobody knows how to write engineers. It's very hard to write the word engineers.
Yeah,
and that's why people switch to be mathematicians. Nobody wants to write down engineers as a major. But then I remembered it's engine. Engine ears. So
It's
anyway.
really annoying because English
It's
is
a side though. Yeah.
English is technically my second language. I forgot my first language, so I have a slight accent in the language I no longer speak.
Oh, that's funny. Yeah, it's true. So, let me tell you about the formula in the homework. And then before I do that, finally I can explain you why it's so cool. Why inverse functions are important. In fact, there are inverse problems still not solved in our world that will earn you Nobel Prize. Oh, you had a question?
Yeah, so I was kind of confused about why the inverse of a function is not the same as 1 over the function. Because usually when you say you're talking about the inverse of a number, it's 1 over the number, right?
Yeah, they just decide to reserve it.
Yeah, so is that just like arcsine, the difference between arcsine and cosecant?
Oh, I think I got the question. No, it's a very good question. Sine minus 1 and arc, this topic I think goes next week. Arc sine of y is the same thing. Moreover, I keep changing between them without noticing. That's the same thing. And I think that's why they decide to do arc sine, to just not to put minus 1 in it.
But then 1 over sine.
1 over sine is different. So it's not the same as 1 over sine. Yeah. So if you have name of the function, sin L-A-N, that's name, right? That's what actually took me a while to understand. All those words we know, that's a name. Isn't it crazy? So, like in my language, we don't call it sine, we call it sinus. It's a different name. So if there's -1 on top of that name, that's inverse. So -1, it's part of the name now. It's not 1 over anymore. That's the idea. They just improved the name, I guess, for specific notation.
So
Yeah.
it's just notation.
Yeah,
Not
it's notation. Later we're gonna learn a hat. Later we're gonna learn a star. In calculus 3 we're gonna have different products. One is dot, the other one is cross product. So there's lots of cool notation coming after that.
God, I hated hat.
No, it's gonna be good.
I have
You-
to say hat when you have to.
Now you will like it.
It's like imaginary numbers are the length of the sides of a negative.
Oh yeah, we're not gonna do imaginary actually in calc 1, 2, and 3 at all. But I know what you mean. Yeah, imaginary hard.
Length of the sides of a negative square is just so hard to picture.
Inverse. So inverse functions can get you a Nobel Prize or recognition from the whole world. There are several famous inverse problems, not functions, that are still not resolved. The inverse function idea is you see the result, but you cannot find out what caused the result. So sine of, you see sine x, and it equals to 1. What caused sine to be 1? Do you know? Sine x equals to 1. The question is, sine of what gave you 1? Pi over 2, for example, right? And others. So you have the result and you know the model. The model gives you that result. But what input in a domain gave you that result? And the most complicated inverse problem of the world is cancer. We have result of cancer and we have lots of models that's actually very nicely explaining how cancer works, how the cell mutates, how they communicate, how they divide and so on, how they are hungry and they're not dying and then keep multiplying. But what causes it? That's the pure inverse function that will someday will be resolved and will have the recognition around the world. What causes it? We know causes of cancer is some kind of food and radiation. But what moment, what was that input that changed from 3 to 7 and cancer started? Do you understand how cool is that? That's a pure inverse problem. The famous inverse problem is about in the criminology. As a criminologist, you show up, there's a dead body. That's the result. And you have formulas that tell you how fast the body cools down after being dead. And because of that formula, people know how many hours ago the person was killed, right? So that's literally the inverse problem. You have the result, you have a formula. What input gave you that result? Oh, it was 3 hours ago. There's so many things. How do we know how old the earth is? How do we know how old the tree is? It's 3,000 years old, but I never cut it. That's the inverse problems here. So it's pretty fascinating. Now, how fast the inverse function is changing. Sometimes if you don't have the inverse function derived in front of you, and then, or maybe just complicate to take derivative of it explicitly, you don't do it at all. Instead, you use this formula. You do 1 over derivative of the original at inverse at x, like so. And this x is input of inverse. So it's domain of inverse. This is a complicated formula. You will have, we were doing it already last time in office hours, examples with this formula. Department loves putting them on a test. I can tell you right now, I'm not gonna put this formula on a test. Students just don't do well with it. It's just, no matter how much you practice it, when you freak out, you, me, your neighbor, when we freak out, this formula just doesn't, right? I know, yeah, exactly. It doesn't work. It just doesn't work. So I see those problems in a test, and then I select them, and I click delete, and they will never get me back again. So just letting you know, do your homework, but I will not put this problem on the exam. And I know it's gonna show up there when I receive exam, and it's, if they complain, I always have something to say, so it's whatever. Does it make sense?
Yeah.
Last couple formulas. So you can start the next homework. And those formulas are pleasant, okay? This chapter is amazing. That's my favorite chapter, is 3.3. So we did 3.1, 3.2. I just merged them together. We had the definitions of limit and log. We had properties, domain, limits with those things, inverse, derivative of inverse. Finally, we're gonna go to good stuff. What is freaking derivative of the log? And what is not freaking derivative of e to the x? E to the x is e to the x. Log is 1 over input. So input, no matter what it is, the inside of the log gives you 1 over that input. E to the x is nice. It copies itself unless there's a chain rule involved. That will be also interesting. And the other two formulas are more annoying because they don't work with classical logs. What if... Yeah, minus also. What if log has a base? So what happens with the base? Well, it's still going to be 1 over x, but also times natural log of a. What is happening with a to the x? It still copies itself, but then times natural log of the base. So formula with e to the x is actually coming from the general formula. E to the x prime copies itself times ln of e, but ln of e is 1. So actually, that's how it was derived. Your job is to memorize these for the rest of your life, basically, until you retire and you don't need STEM anymore. They will be everywhere, promise me. In architecture, engineering, space science, biology is everywhere. The other two you also need to memorize, but it's mostly for this class only. To be honest, I don't like testing people on these formulas, but I will see how strict this is in this school.
What's the difference between the last two?
The last two, that's example. You mean this one? So example, if you have e to the x, how do I know it will be just e to the x? E to the x prime is e to the x times ln of the base. That's coming from the main formula. But ln of the x, ln of e is 1. And that's how the formula was derived. But you know what's interesting? See, I have like 5 minutes to get excited. This is the most fun part. What if there's a chain rule involved? So if we have e to the u, and u is the function, you copy times derivative of the function inside. And the function inside, in this case, is in the exponent. And let me show you the next one, and I'll give you 2 examples. ln of u will be 1 over u times u prime if u is a function. That, what rule is that? Chain rule. Your biggest nemesis, chain rule. When I ask Calculus 3 students what do they think about chain rule, they still don't like it, even in Calculus 3. And we're going to have a multidimensional chain rule in Calculus 3 with 4 dimensions and 5 dimensions and more than that, actually. So, to explain you what it means, it's not as bad as you think. E to the 3x prime. How fast is e to the 3x? It's e to the 3x fast times 3 times derivative of the function inside. But derivative of 3x is 3. So that 3 adds a rate. It's not adds, it's a factor of the rate. So it's e to the 3x fast times the rate of the exponent. And the rate of the exponent is 3x. And it can be anything. E to the 7x squared plus sine x. Do you think that is hard? No. That's the thing, like my job is to make you feel confident about this. You can do it. It's the same idea. It's not easy, but the idea is the same. You can do it. You're very smart. Copy, no matter how crazy it is. And then guess what? Times, just like before, the derivative of the function inside, 14x plus cosine. Can you do that? You see, this is already on the test, master exam and the final, and you already can do that. So I always like to mention this idea that you are working hard on this homework and you feel frustrated. The Weber gives you this red, not correct, and you feel like it says you're stupid, quit it. Yeah, let's just try to fight it, okay? Don't be upset. Keep working, because I know that you can do it. That's like the best feeling. I already see you can do it tomorrow and the next week. So your job is just not to give up. If you don't give up, I promise you, you will do it. That's my suggestion. So now you can start homework 3.1, 3.2, 3.3, and I will see you on Friday for the quiz.
have